Swayam Prabha. Digital India. Educated India.
Now identifying the visits to states, like often when we have a Markov chain, right, like it is going to be taking different states, fine, I may be interested in when is the first time it is going to visit the particular state, and to visit that state possibly on an average how much time I am going to spend. Okay, so such questions you may be incurring, right. For example, on an average how many times my share price crosses a certain number, and you want to understand the distribution of such counts. So for that we have this notion of hitting times and recurrence. Okay. Now let us take a state I and state j. I am interested, let us say if I start from state I, when is the first time I am going to hit state j. Okay. Now I am going to define Fijn as probability that x1 not equals to j, x2 not equals to j, all the way up to x n minus 1 not equals to j, and exactly at xn equals to j given x naught equals to I. So what I have done here, starting from I am interested in hitting state j only in the nth round, not before that. Okay, I am assuming that I and j are different here now. Now I could set n to be anything, right. I could just say n to be 1, that means what, I start from state I and I want to go to state j in one step, or I could state any n positive number, and now this probability is giving me what is the, so this expression is giving me what is the probability that I will go to that state in this exactly n many rounds. P of j, this one is it, this is it Pij of n? What is Pij of n? It is just like it is going, if you start from I and you want to be in state j after n steps, yeah, it does not say that तुम बीच में उसमें नहीं जा सकते हो बोल के. Okay, you can, this one will say that you can't go there in between, this allows that option. Okay, then okay, so now this is what, in a way if I am interested in knowing my first visit to state j here, right, starting from I, my first visit to state j starting from I in n number of rounds. Okay. Now suppose let us say Tn is first visit to state j, and I am assuming that starting from I. You can visit from state I to state j in either 1 steps or after 2 steps or after 3 steps, or maybe like it can go on, right, you do not know how many times. Now if I want to say what is the probability that T1 equals to finite, what is this? What is this probability? So I could go from state I to state j in 1 step or 2 steps or 3 steps or whatever, right. Can I express this in terms of Fij's? What would be that? So अगर 1 में भी जा सकते हो तो ठीक है, 2 में जा सकते हो ठीक है, 3 में भी जा सकते हो तो ठीक है, all these are fine, right. So ultimately I can say that like this can also I can say probability that there exists n such that xn equals to j starting from, eventually I am going to hit state j starting from I, right. So this is nothing but Fij of n, and what is n? N is going to be greater than or equals to. So this is saying I am going to hit n, but right now this is not telling at what round, and you could be hitting in 1, 2, 3, 4, 5. So there exists some h such that I am going to hit state j starting from I. So this is nothing going to be the sum of all these Fij's. Now I am going to denote this quantity as Fij equals to summation Fij of n. Is this quantity is going to be less than or equals to 1 or equal to 1? So I have just showed that this is nothing but some probability, right, probability of some event happening T1. So this has to be necessarily, it is going to be less than or equals to 1. Okay. So okay, now suppose let us consider the case when Fij is strictly less than 1. What does this mean? So Fij less than strictly less than 1 means there is a possibility that when I start from state I will never come back to state j. That is why we are calling it as hitting time and recurrence, whether this is happening or not. Suppose Fij is less than 1, we kind of understand that there is a positive probability that if I start from state I will never come back to state j, I will never hit state j again. And now if Fij is equals to 1, what does this mean? I will come back to state j starting from I in finite steps. Okay. Now whenever, let us consider this case, whenever Fij is equals to 1, that means what? This Fij's does it make a probability distribution on n? See all this, so we know that each Fij of n is going to be greater than or equals to 0, right, this quantity can't be negative because this is a probability here. And if you are going to say this Fij equals to 1, that means this is a vector, I mean this is a infinite dimensional vector and it sums to 1. So this is going to be a probability distribution, right, on what? On n, whether it is going to take 1, 2, 3 or up to whatever value. So this is going to be a distribution. Whenever that is the case, whenever let us say whenever Fij is a distribution, Okay, by the way, when Fij is less than 1, we are going to say that state J is transient starting from I. What means by transient? That means, yeah, I mean if it means it is possible that it will never come back to that state. And when this Fij is equals to 1, I know that starting from state I will surely come back to state J, right? After some time, maybe whatever time it is going to take, I will surely come back to this. Okay, now
You said that Fij of n greater than equal to 1 is a random vector.
this is a distribution. Let me write this we call it as first passage time distribution. This is a distribution taking what values? Discrete values, and what are these values? N equals to 1, 2, 3, 4, right? So probability that it takes 1 is Fij1, probability that it takes 2 is Fij2, and probability that it takes value n is Fijn, like this. Okay, now let us say instead of starting from state I and looking at some others, hitting other state, let us take I equals to j. Now what I am interested in, starting from state I, starting from state j, and again visiting that state. Okay. So in that case, if Fjj is less than 1, that means if I start from state j, there is a possibility that I will never come back to state j again. And if Fgj is equals to 1, that means if I start from state j, it is possible that I can come back to this. So for example, let us say that your share price of a particular stocks hits some 100 rupees, then the probably, so let us say its base price started from some 100 rupees, probability that it come back to 100 rupees again, if that state has Fjj value equals to 1, that means it is going to come back the probability 1 again to state 1. And then if this Fjj has value 1, that means that it will never hit that 100 rupees value again. I mean with some positive probability it may never hit again. It may hit, but there is also chances that it may not hit 100 rupees again. Okay, now I know when Fjj equals to 1, this Fjj of n's forms a distribution. In that case, further I am going to define another quantity called expected value, which is defined as Fjj of n. Now this Fjj is a, so what is this Fjj n? This is the probability that the first time I am going to hit state j again in n rounds. So what is this is going to give me? Expected time to hit state j again, okay, expected time to return to state j. So when I have this Fjj, this Fjj I am going to call it as probability of first return to state j. Okay, so I am calling it return because I starting from state j and again looking at coming back to this, right, or returning to that state j. And this is mean return time. Now, as I said, let us take a j s. Now we can classify that state based on these observations, right. Suppose if my fjj is equals to 1 or my fjj can be less than 1. Further, when my fjj equals to 1, two things can happen, right? That is, my vjj can be, new jj can be finite or my new jj can be infinite. So, as I said, when fjj happens to be 1, we are going to call that state j as recurrent, because we have a positive probability of coming back to this. And when fjj is less than or equals to 1, that means it is transient, matlab it may come back sometime and then die out, it may not come at all, right. So, in that case it is transient. Now, when it is recurrent, yes, we know that it is going to come back. Now, the question is whether it will come back soon with high probability or it will come back but after a long time. So, when you know it is going to come back, now you may be interested in knowing the frequency of coming back, right, in a way. It is going to return quite often or it will return but very rarely, right. You may be interested in these two scenarios, right. So, when it is going to come back frequently, what is the case you expect this mean return time to be? It will not be large, right, in that case. It is coming back frequently, so that most of the times maybe n are smaller, and those smaller n will have higher probabilities, right, and the larger n's will have smaller probabilities. But on the other hand, if this guy is not returning so frequently, it will coming up very long time, or this is happening very rarely. That means the n values which has having positive value mass, right, those are going to be very large. So, because of that this vjj may be large or may be unbounded also. Okay, so that is the case we are going to distinguish here. So, when it is recurrent, yes, we know it is going to come back, but whether it is going to come back frequently or it is going to come back rarely after a long time. So, if it is going to come back after a long time or it is going to come back rarely, we are going to call this as null recurrent. And then we are going to call this case as positive recurrent. Okay, let us assume that you are in an insurance business, okay. You start with some capital money, whatever you are. Now, how the insurance guys will work? They will all charge you some premium, right, and whenever you get into trouble, you go back and ask for coverage, and then they will pay you from this. So, what insurance guys like? They like that you pay regularly the premium and do not come back and claim anything ever, just keep paying, okay. So, but anyway, they are supposed to pay you when you are in trouble. What if some tragedy happens and a lot of claims come? If lot of claims come, insurance company has to reimburse lot of money, right, and their balance may go negative also. So, suppose let us say, so in that case what an insurance like company want to do? It want to make sure that at any given time its capital does not go below some threshold. You keep paying premiums, its capital keep accumulating, but at some point if large claims come and happen, and small claims are fine, like everybody is paying premier, some guys claim some coverage, the capital may be still growing, but if sometimes large claims come, their capital may start going below, right. So what insurance companies want is, they do not want to go bankrupt, right, they do not want their threshold to go below some level. Maybe if it goes once or twice, it is fine, but if it happens often, maybe they can't survive in that business. So let us take such a, let us say insurance company is going to define some states. If my capital is this much, this is my state, if my capital hits this much, this is some states, let us say some states, and they will define one state which is, they call it as, let us say a danger level. If my capital goes bit danger level, that means I am in danger. Now what that state the insurance company likes to be? They want it to be happen rarely, right, they do not want it to happen often, yes, some. So in that case, if you are going to model that case, you want, if your capital, whatever the state you are going to define, if it happens to be a null recurrent possibly, then you are going to enter into, if you are initially a planner who want to get into this business and you have some capital with you and you have to decide, okay, whether I should enter this matter, and let us say you are able to model all these things and come up with all these distributions, and then you are able to also compute the expectation. Then the question is, okay, should I enter? If you a priori feel that no, it looks like my state of getting into danger happens to be a positive recurrent, so this looks a very risky business, I do not want to get into this. Okay.
Why even null recurrent? They want to be
So say like calamities you can't avoid, right, like I mean so far whatever, like let us say for some reason some big tragedy happens and you can't say that the tragedy will not happen again, right, and it can happen, not in our control, but yeah. Yeah. So what? Okay, fine. This FJJ. So FJJ is one that is means if the risk some calamity has happened today, you can't guarantee that the calamity is never going to happen in the future, right, it may happen in the future. So you are going to visit again, that is what FJJ1 means. It is not saying that so FJJ is equals to 1 means you can't say that nothing bad happens in the future. It can happen, but it may happen after a long time or short time, that is what now matters to you.
But that can happen in FJJ less than 1 also. So FJJ less than 1 is the finite probability that nothing bad will ever happen. It is not possible. It is not 0, now it can be 0.7. So there is a 0.3, there is a probability that nothing bad will ever happen. It is not possible, right?
Now FJJ equals to 1, it is just saying something bad will happen, but the rate at which it is going to happen, what matters to us, right. If the bad things are again going to come again and again very frequently, then you are, I mean say here that is the opposite, right, here this bad things are actually good things here, because we are talking about this n to be large means okay, so when n is equal, so what is this, when n is equals to large, that means bad things are happen only very later, that means actually null recurrent is good for you. If the bad things are happening very frequently, that is a bad thing for you, that is the other way around here.
What I am saying is that if we are in transient,
if you are in transient, yes,
FJJ for example is 0.7, so it means bad things can happen with probability 0.8, 0.7.
yes, and actually you are in a good case, like, and also like I mean it depends on the value of FJJ, it also says that you may never see a bad case again with 0.3 probability, yeah, exactly, Yeah, exactly. So that, so as a modeler you do not want to assume that, it is basically assuming that okay, with some positive probability nothing is going to happen, bad is going to happen in the future. You have to account that okay, something may happen, but that may not be that frequent. Okay, so this is all again the design choices, like how risky or how risk averse you want to go for it. Based on that you are going to set these values. Okay. Okay, one more thing before we compute the other distribution. So let us say this Fijn, right, we know this is not Pijn, okay, but can I compute this quantity only using my transition probability matrix TPM? Why is that, if yes? So what I need to know is okay, x naught equals to I am not coming back to state j till nth round. Can I compute this probability using transition probability matrix? Verify that, yes, I mean this is just like you need to just argue that yes, we can compute this probability Fijn using only transition probability matrix. So all this characterization of whether my state is transient or recurrent and further positive recurrent, null recurrent, this all can be explicitly stated just by knowing your transition probability matrix. Okay, next. Okay, maybe before that let us look into this example. Okay, I know, let us say I have been given some simple Markov chain with 3 states, and I am going to express its transition probability in terms of this transition diagram like this. So I have written in terms of a transition diagram, you can also express in terms of the transition probability matrix, the same thing. Okay. Now can we compute F0 1 yeah. So what does this say? That I start from 0 1 and I hit state 1 in one step. What is this probability? That is going to be 1 minus p. So this is the only path, right, first time I am going to do. And now if I want to do it in 2 steps, p into, and if I want to do it in n steps, p to the power n or p to the power n minus 1. And now can you give me what is f of 0 1, f0 1? The summation of all will be what? So right, this is going to be, yeah, so there will be infinite, so it is going to be 1 minus p into summation of p to the power n, where n is going to start from 0 to infinity, and that is, yeah, just work out, this is straightforward. And now what does this say? That if I start from state 0, that I go to state 1 is going to be 1 with probability 1 I am going to hit state 1 at some point, and because of that my state 1 here starting from 0, it is going to be a recurrent one. Okay. And now similarly maybe you can just also 0, okay, now let us see if I want to do 0. So what is this probability that I go to state 2 starting from 0 in one step? 0. And what is this is going to be? So the only way I can go from here to here is this route, right, in one step, when in for the first time, and then f of 0 3 is going to be what? So I want to go from here to here in 3 steps. So one possibility is go from here and then stay here and then go here, right. So what is that probability? 1 minus p into 1 minus p. Is there any other possibility? So you stay here in the first round on 0, then you go here. So what is that value? P into minus p. And is it possible to write generally this one for n? So I want to do it in n steps. No, in n steps. Zero to 1? No, you keep first time. It's not all possibilities we are looking at. Okay. So I compute this, then you have to just basically work out in how many possibilities. So one possibility is just like go from here to here in one step, stay back here for n minus 2 steps and then go there. Then other possibility is you spend n minus 2 steps there itself and then go here. But there are other possibilities also, right. You can spend one step here, go here, then spend another step here, like or whatever, like. So there are many other combinations which you can write down. Okay, so as you see that, and even for the simple things, writing this can become too much of a combinatorial issue. You have to look at all possible paths that you can go from one state to another to reach it for the first time. Okay. Okay, now let us compute this. So one thing is the number of rounds required to hit a particular states, and other thing is when you are going to run it continuously, how many times you are going to revisit that state, right. So revisit or return to that particular state. So suppose let us say I have a state j and I am interested in just a minute, yeah. In this? Okay, just to clarify here, to the way we have defined the recurrence, transient and all, right, we have stated like okay, you start from that state and again see visit to that state. But here what we have done is we have taken some initial state which could be different from the state we are going. So if you want to, in this case you have said f01 equals to 1, that means if you are going to start from state 0, then state 1 is recurrent in this, right. So instead of this you can also compute what is f11. You start from state 1 and then again look at coming back to this in 1 rounds, 2 rounds or 3 rounds, whatever. So is it easy to check this? Let's say let's compute this f00. Suppose if you start from 0, what is the probability that you come back to that state in one step? P. And then what is the probability that you come back to that in 2 states? 0, right. So what is that in that case? This is going to be simply all other terms are 0, right? You came back one times, but once you left it, there is no return part to 0, right? You are not going to come back to that again. So this is going to be simply P in this case. If suppose P is less than 1, what is state 0? Transient, right? That is obvious, right? एक बार तुम इधर से हट के state से, then you may not come back to that state again. And if P is equals to 1, then in this case it is trivial, like you will be always in that case. So like that you can compute for all the states, and then based on that you can classify which one is transient and which one is recurrent, and the recurrent one you can further classify whether it is null recurrent or positive recurrent. So to compute all this, all you need to tell you these transition diagrams or your transition probability matrix. Okay, now look at this. What is this quantity guy is telling you? So what is this? This is going to say 1 here if nth state is j. So what is this term is telling you? Number of times you are hitting state j, okay, over the entire process. So that is why this is called number of returns to state j. And now I may be interested in computing expected value of m of j starting from a particular state. Okay. Now what is this going to be? Expected value of can anybody now see now this is a limit, right? What so this is nothing but what I can write it as expectation of is this correct? So this is nothing but n equals to 1 to infinity, right? I mean, let us assume this limit exists. Limit as n goes to infinity s1 to s this one. Now we are faced with, now I want to interchange this expectation and this limit. Can I do so here? Can I do so in this example? So let us say I call this as something as yn, okay. So I have this sequence of yns and I have limit as n goes to infinity of this yn, and now I want to interchange this. Right now I do not know where this yn, the sequence yn converges in any of the senses. All I want to do is I want to check whether I can interchange this limit and expectation. When I can do this, if at all I can do this. We can apply what results? Monotone convergence theorem. You can we apply here in this case? So okay, limit to interchange limit and expectation, what all the results we have studied for a sequence of random variables? Yeah, bounded convergence theorem and dominated convergence theorem and monotone convergence theorem. So to apply bounded and dominated convergence theorem, what are the hypotheses we needed? That is one thing, and we needed xn to be converging to some x in probability, right? So we needed to know that sequence xn converges in some sense. But here, and what is the last one? Monotone convergence theorem. To apply that, we did not need to know what is the limit of my sequence. All to what is the hypothesis to apply my monotone convergence theorem? Non-negative.
x1 of omega should be less than equal to x2 of omega.
Yeah, for each sample point my process should be sample point. Is that happening here? Why is that? Summation of indicators, right? So indicators are all non-negative values. So if you increase n for a given omega, it is only going to increase as n increases. So I can apply my monotone convergence theorem and then interchange limit and expectation. But then this one is a finite, there are only finite sum, I can further interchange this. Yeah, given, right, and then I can interchange that this is going to be s equals to 1 to n. What is expectation of indicator that xn equals to j? Probability of xn equals to j given what is this? Is it xn equals to j given x not equals to I, right? And what is this by our definition? Pij, right? And this is nothing but I can write it as n 1 to infinity. So my mean number of visits to state j starting from I can be expressed as simply as Pij of n's for n going from 1 to infinity. Okay. Okay, fine. So let's stop here. Next class. So what we have just now done is we have just written the expected value of this mj. In the next class we will also try to see if we can derive the distribution of this mj itself. Okay, mj is the random variable here which takes any value between 1, 2, 3 up to infinity, right? So how to find its distribution? We will see that in the next class.